So these are the homework questions and problems in chapter 30, which is leading into circuitry, but not necessarily quite there yet. Deals with kind of current flow and things affecting that. And I know some of the formulas in this chapter are a little odd. There's a couple of them. E equals rho times J, for example, and is one of the two that are on your formula sheet that tend to be not used too often, and understanding what those variables mean can help you know when to use those. So the conceptual questions I think we all went over in class. I'll upload a PDF of my answers on my website also, as I always do, but I think these are here. One of the classes we did have a little bit of confusion that really the radius or diameter was labeled as these things. That's supposed to be an R, not an N. And so we have to really look at the area. So it's proportional to R squared. For the problems, I know a lot of people had confusion with number 2. This formula was in your textbook, slightly different than the one on your formula sheet, basically because this is electron current. If you had converted this to regular current, which is coulombs per second, then you would have had a conversion factor here as well. In other words, instead of just charge density, which is this in iron, you would have had charge density times the charge on a single electron, which is 1.6 times 10 to the negative 19th, would have given us the same drift speed. But basically that's units here of electron flow versus current, which is coulombs per second, as opposed to charges per second. 13, pretty straightforward. If you have something with 10 amps and you want to find out how many electrons move in a given amount of time, in this case 5 minutes, you convert the number of charges per coulomb times the time. And again, that's a big idea, is that 1 amp is 1 coulomb per second. For number 21, this is the second formula on the sheet. Like I said, basically current density is I over area. So coulombs per second, meter squared. So in this particular case, when you're given the current, you can calculate the area up here. So we get this current density, which I didn't do as a separate calculation. I embedded it within this thing overall. And so we get the resistivity that way. Again, a little obscure. If we have two objects, one's twice as long and twice the diameter of the other, it's asking you to compare the resistivities and the resistances. Resistivities would be the same if it's the same material. So in a way, resistivity is a property of the material. That's very much like coefficient of friction, which is a particular interaction between two materials, though. It's like density, which is specific to particular materials and whatnot. So if you have a wire 2 times as long and 2 times the diameter and radius, that would be basically 4 times the area. So we would use this version of the resistivity and resistance formula, which you should be pretty familiar with. We're using that in the lab, and we would go from there. For P29, using that formula again, getting the area based on things that are known. Be careful because I think they tell you the diameter here is 0.8 millimeters, so I immediately switch that to radius and immediately switch that into meters, which are standard units, and then can get the resistivity and then go to a table and find what the material is. 34 gives you the potential difference, length, diameter, find the current. Again, so the key thing here is if I want to find the current, I need to know the potential difference, which is 9 volts, and the resistance. So I've got to find R. I use the resistivity formula for that, similar to what I did in the previous problem. Get that resistivity of carbon from the table again, get the resistance overall is 5.46 ohms, and then go to find the current. 52 is a reminder that there's still a little bit of calculus in this part. There's calculus in 2 other parts of E&M, not as much with circuits. But it basically is the rate of change of charge over time. It's a rate of flow, so that is a derivative of the charge with respect to time. So if the charge total is described by 4t minus t squared, the derivative of that is 4 minus 2t. If I plug in times of 0, 1, 2, 3, and 4 seconds, this is the graph at which I get. So it basically says the current switches directions. Final one, which I like, it's a nice picture I drew for me. You've got a single battery here. Sometimes voltage is shown as a script E, as an EMF. The archaic term was electromotive force, but it's not a force. But you can think of it as the push, in a way, that causes electricity to flow. It's basically caused by the creation of an electric field. At any rate, it says the current through here and the current through this unknown resistor is the same. What's this resistance? Well, these two batteries are in series, so this would have a potential difference of E. From down here to up here would have a potential difference of 2E. So if you have twice the voltage and they're both series circuits, this would have to have twice the resistance to have the same current. So hopefully that makes sense, and I'll upload it.